So let's move on and have a look at some work to do with collisions. Well, first off, how do we prove collisions? For a collision to take place, we know that the two objects need to occupy the same space. However, this requirement is not sufficient to guarantee collision. All we have to do is to look at this example, and we see that one object just passes behind the other object. So they do pass in the same place, but they just don't do it at the same time, and time is the key. In order for a collision to take place, the two objects need to occupy the same space at the same time. What does this mean in terms of vectors? Well, for objects to occupy the same space, they must have the same I component and the same j component at the same time. It's important to note that objects can have the same I or j component at a given time and still not collide. So here we notice that the I components are equal, the j components are equal, but there was no collision involved here, and the reason for that is that the time values are very different. So how do we prove collision? Well, we have two options. Option A, equate the I components and find a value for t. We can then substitute this t value into our equations and show that the displacement is going to be equal for both. Our option B starts in the same way as option A. We need to equate the I component to find a value for t. We then equate the j component to find a value for t, and we just simply show that these t values are equal. Now I'm going to show you two examples using each method. In the first example, we've got this case, so I'm just going to write this down using column notation, so that's to say that my starting point is going to be 0, 9, and I'm going to be adding on t lots of 2, negative 2, and that's going to give me the general position of vector A. For the general position of vector B, I'm going to have 6, 1, plus t lots of minus 1, 2. I really like this column notation because it's just so powerful, and equating the I components then just becomes a matter of looking at the top lines of these equations. So equate I, and if I equate the I components, I find out that 2t would be equal to 6 minus t, or to solve that, 3t would be equal to 6, or t is equal to 2. Now for option A, I then take that value of 2 and I evaluate these at the time t is equal to 2, and that's what I mean by drawing this long vertical line. It means evaluate the position of A at the time 2. So that's going to be 0, 9 plus 2 lots of 2, negative 2. And what would that give me? That would give me 4, 5. Or in vector format, that would give me 4i plus 5j. Now I need to do the same for the b component and evaluate that at the time t is 2. What would that give me? Well, that would give me 6, 1, added 2 lots of negative 1, 2. And 2 times negative 1 is negative 2, so that gives me 4 and 5. Unsurprisingly, we're showing that the two things collide, and they certainly do at the point 4i, 5j. And that's exactly what we've got here. Our two objects come to collide with each other. Now, in the next example, we're looking at exactly the same setup, so I'm using exactly the same equations for both example A and example B. My method of solution is just slightly different. Now if we remember back, option B just required me to equate my j components and to show that the time values were equal. Well, I've already equated my I components, so I know that the answer for that is going to be 2. So now all I need to do in the next part is just equate my j components. So let's just jump straight into equating j. And that would be to say that 9 minus 2t would be equal to 1 plus 2t. And rearranging this, I'd find out that 8 was equal to 4t, or that 2 was equal to t. And again, we've got that same value for time, so again, collision must occur. Let's now apply this to an exam question. We've got a boat that's moving at a constant velocity, and we're given that at time t equals 0, it's at this position vector. So let's write that information down using column notation. So the general position of A is going to be 2, negative 10, plus t lots of minus 1, 6. I'm then told about a second boat, which is boat B, so I'm going to write that down as the position vector of B, and that is generally at the point with initial vector minus 26, 4, plus t lots of 3, 4. I now need to show collision, and I want to find the position of this collision. And because I want to find the position, I'm going to use option A as my method. So that starts with equate I, and if I equate the I components, again I can just look at the top rows and it comes out so easily. 2 plus negative t is equal to negative 26 plus 3t. Solving that, I've got 28 is equal to 4t, or 7 is equal to t. Now I'm just going to go through and evaluate both of these at t is equal to 7. So that is to say that r of a evaluated at t equals 7 would give me 2, negative 10, and 7 lots of negative 1, 6, which is 2, negative 10, plus negative 7, 42, which would give me negative 5, 32, or as a vector, minus 5i plus 32j. Now I haven't shown the collision yet because we don't know where B is, so we better do that now. What position is B in? Again at the same time t is equal to 7. Well, that's going to be negative 26, 4, plus 7 lots of 3, 4, which gives me negative 26, 4, plus 21, 28, which is equal to negative 5, 32, or again in vector form, minus 5i plus 32j. Hence we have collision at the point P, so we can just say that P is equal to negative 5i plus 32j. And that's the end of everything we're going to talk about. Thank you very much.